Let us now sketch the graph of f of x equals x logarithm of x. We are going to use the guidelines that we saw last week. Okay, so if you want, you can now pause the video and do by yourself, and then we can compare notes. Okay, so the first thing we need to do always is to compute the derivatives whenever that's possible. So this is 1 times the logarithm plus x times 1 over x. So that is logarithm of x plus 1. And then the second derivative becomes very easy because it's just 1 over x, because the plus 1 doesn't really bring anything. Okay. Now we have the derivatives, and then we need to start getting information, collecting information. So the first thing we notice when we look at this function is that there is a logarithm. And that means we know the logarithms are picky, right? So we need to see what is the domain of the function. So for the domain is 0, infinity, right? Because the logarithm will only take strictly positive values of x. Okay, 0 is excluded because for 0, the logarithm is negative infinity. Now the critical values. Those are the solutions of f of prime equals 0. That means the logarithm of x equal -1, right? And that means x equals e to the -1, or 1 over e. Okay, it's the same thing. All right. Now, we can also, as we are computing, we can also see the intervals where the function is increasing or decreasing. Remember, f prime of x bigger than 0, that means f increasing. This is if and only if logarithm of x plus 1 is positive. That means logarithm of x bigger than -1. That means x bigger than e to the -1 equal 1 over e, and decreasing otherwise. Okay, so here we are ready to do a sign chart for f. Remember that we are only concerned about x in the domain. Okay, so we will have to take 0 here, then 1 over e, and we will only care for the values towards infinity. Okay, so we have that f is positive. Sorry, f prime is positive when x is bigger than 1 over e. F prime is negative otherwise. That means f decreasing, then f increasing. Okay, so we conclude that 1 over e is a local minimum. Now, for the inflection points, now we are going to study the second derivative. Here we are going to compute f second equals 0, right? The second derivative was 1 over x. 1 over x equals 0, but this is not going to happen. Okay. For this to be true, x would need to be infinity, but that's not a point. Okay. So this is impossible. So there are no inflection points. no inflection point. And now we need to see the intervals of concavity. Now, because there are no inflection points, we already know that the concavity is not going to change. Okay, so it will be concave up or concave down in the whole domain, and that's it. Because it cannot change, because if it changes, then we would have some inflection point by definition. Okay, so let's see. The second derivative is 1 over x, and x is positive, so the second derivative is positive. So that means f is concave up. Okay. And here we have all the information then. So we can go ahead and draw our axis. I didn't like that. There we go. I'm going to need more space, like this. And here, some information we have is that the function is decreasing all the way to 1 over e. So f is decreasing here, and then it's increasing. And we have that f is always concave up. Now notice, because the second derivative is positive at 1 over e, that is telling us that that point is a minimum point, a local minimum. Okay, that we already know. So local minimum. It may happen that it's an absolute minimum. Actually, it has to happen because f is concave up, so it cannot go down. Okay, to go down, the graph would need to bend and be concave down. But for that, we would need to have inflection points, which we know we don't have. Okay, so f of 1 over e, this is 1 over e logarithm of 1 over e. So that is minus 1 over e. Okay, so it will be somewhere here. Okay, minus 1 over e. So the function passes through this point. And then we can probably put this information here. There we go. And then we would like to know also what is the limit as x tends to 0 of x logarithm of x, okay, which is of the type 0 times negative infinity. This is not of the, this is an indetermination, but it's not a L'Hopital type of thing. But we can turn it into L'Hopital, so we can write logarithm of x divided by 1 over x, right? This now is negative infinity divided by infinity. And L'Hopital is going to say, okay, this is the limit of 1 over x divided by negative 1 over x squared, okay, which is the limit as x tends to 0. I should say from the right, sorry, all the time, okay. So this is negative x, and that is 0. Okay, so the limit as x tends to 0 is 0. So that means the function will fall here, will tend to this point. And then something else that we need to know is the limit as x tends to infinity of x logarithm of x, but that we know because the limit of x is infinity and the limit of logarithm of x is infinity, so this is infinity. So it will just go up. And that's all the information we need. So we know it's concave up, so it will look something like this. Let me use a different color. And then it will go up like this. Okay. Notice something that I didn't realize, but the function has to cross the axis. So it will cross the axis when x logarithm of x equals 0, right? So that will happen either x equals 0 or the logarithm of x equals 0, which means x equals 1. So this value here is x equal 1. Okay, and that gives a complete picture of how this function is going to look. Now we can check our work looking at the calculator. I plotted the function here for you. So you see that it's exactly what we got. Okay, it's the same shape. It's clear that we have an absolute minimum. Then we have a 0 at x equal 1, and then the limit is clearly 0 as x tends to 0 and infinity as x tends to infinity.